The NMR spectrum contains certain regions, just like the IR spectrum contains certain regions. So depicted here is a diagram of where you would expect the NMR peaks of certain types of hydrogens and certain functional groups to come. And at least in my class, you will have this diagram with you on the exam. But in terms of working lots of NMR problems, you will need to start to get somewhat of an intuitive sense of where to expect certain types of hydrogens when you see a spectrum. So what I want to do is go over this diagram a little bit and start to explain to you why you get certain peaks in certain regions. Okay, so to start with, carboxylic acids and aldehydes have their peaks way downfield between 9 and 12 ppms. Hydrogens on aromatic rings are generally in the region from 6.5 to 9 ppm, so I would actually extend the aromatic region all the way down to 6.5. And then hydrogens on carbon-carbon double bonds, right on the double bond in an alkene, is in the region from 4.5 to 6.5. So all of these downfield hydrogens are part of functional groups with pi bonds. What happens is the electrons in those pi bonds cause a local magnetic field that's in the same direction as the applied field at the location of those hydrogens. This negates some of the effect of the shielding that we talked about in the last lesson and shifts peaks downfield a little bit. Everything else, what we're going to call the aliphatic hydrogens, that's the term that chemists use from it, show up in the region between 0.8 and 4.5 ppms. Since there's a lot of stuff in this region, I want to go over this region in a little bit more detail. So the downfield end of the aliphatic region, the region between 3 and 4.5 ppms, is where you find hydrogens on carbons next to electronegative elements, such as nitrogen, oxygen, or a halogen. Okay, look back at this. That's this region here, hydrogen on a carbon bound to a nitrogen, oxygen, or X's halogen. So that region is kind of unique by itself. We'll get to OHs and NHs at the very end of this lesson. Okay, why is this? Well, electronegative elements tend to draw electron density in bonds towards themselves. If the electron density is drawn towards a nearby electronegative element, there is less electron density on the hydrogen. So therefore, that hydrogen is more electron poor, and we know that electron poor hydrogens are further downfield, so they are shifted to the downfield end of the aliphatic region. The middle part of the aliphatic region is the region between 2 and 3 ppms. And the common trait about this region is that this contains hydrogens 2 bonds away from a double bond. So we're talking about allylic and benzylic hydrogens. Now don't confuse these with alkene and aromatic hydrogens that are further downfield. Those are 1 bond away from a double bond. These are 2 bonds away from a double bond. And the other one that's really, really, really important is hydrogens on carbons next to a carbonyl group. Again, don't confuse this with an aldehyde, which is 1 bond away from the carbonyl carbon. That's down in the region around 9 to 11 ppms. But anytime you have a ketone or an ester and there's hydrogens on that alpha carbon, the carbon next to the carbonyl group, we're going to find those hydrogens in the region from 2 to 3 ppms. And then finally, the upfield part of the aliphatic region is the region between 0.8 and 2 ppms. And this is where you will find hydrogens on carbons with no functional group nearby. Okay, so these tend to be at the ends of chains or, ethyl groups, etc., that don't have anything else nearby. So tertiary is within this region for between 0.8 and 2. Tertiary tends to be further downfield, 1.5 to 2. Then secondary, 1.2 to 1.5. And then finally primary, or methyl, 0.8 to 1.2. Because carbon is slightly more acidic, more electronegative than hydrogen is. So if you have a carbon atom, a tertiary, it's going to have a carbon atom, it's going to have 3 carbon atoms in addition to the hydrogen. A secondary is going to have 2 carbon atoms in addition to the hydrogen. Primary is only going to have 1 additional carbon atom. So because carbon is slightly more electronegative than hydrogen is, those will appear slightly further downfield. Finally, hydrogens on oxygen or nitrogen. If you look back at that chart, they have a very broad window because they can show up just about anywhere. And in fact, OHs and NHs show up in very different places depending on factors such as concentration, solvent, and temperature. So they're not terribly diagnostic. They also tend to be very broad peaks. Okay, so in the next lesson, we will start to talk about the spin-spin splitting.